This conference will now be recorded.
Hello everyone. We will start with problem, but after that, the topics that we are going to discuss is dual nature of electromagnetic radiation, continuous spectrum, line spectrum, band spectrum, emission and absorption spectrum, line spectrum of hydrogen atom, and there will be also some related problems. Here we have this problem. It is saying that if work function of a metal is 6.63 into 10 to the power minus 19 joule, find minimum wavelength of light required to emit photoelectron. Fine. So in photoelectric effect, one equation we have seen, and according to that equation, h nu equal to h nu naught plus kinetic energy half mv squared. Now in this case, as it is mentioned, minimum wavelength of light required. That means minimum wavelength means what? Maximum energy. Okay. So this minimum wavelength, when it is saying, that means whatever energy is provided to us, that will be completely utilized just for the ejection of electron. No extra energy will be left for the kinetic energy of the electron. So this nu, that is actually we are providing, or you can say the wavelength c by nu that we are providing. You can express it in terms of nu or in terms of lambda. So I'm writing it in terms of lambda, hc by lambda, then hc by lambda 0. Now this lambda 0, it is corresponding to this threshold frequency and kinetic energy. Now when it is saying that minimum wavelength, that means here you have to consider kinetic energy is 0. So whatever energy we are providing, that is completely utilized for this part. So that is why this is, we know this is work function. Work function is expressed as, sometimes it is expressed as W, or sometimes it can be also expressed as phi. Both are fine. So here phi is equal to h nu because kinetic energy is 0. So now we can write that hc by lambda, that is equal to phi. Okay. Now if hc by lambda equal to phi, and here value of phi is given, which is 6.63 into 10 to the power minus 19. So now we can write this equation. So according to this equation, as kinetic energy, you can also call it maximum kinetic energy, both are fine, as it is 0. All the energy that we are providing, it is completely utilized for the ejection of electron. So that is why it is 0. And phi will be equal to hc by lambda. And this value is given 6.63 into 10 to the power minus 19 already in the question. So we need the value of lambda. H and c, these two are constant, their values are known. So phi is equal to hc by lambda. That means lambda is equal to hc by phi. That means hc by work function. So this is the value of work function that is already given in the question. This is the value of h, Planck's constant, 6.60 10 to the minus 34. You can also write the unit joule second. And this is velocity of light, which is having unit meter per second. Okay. And this is also having unit of energy, joule. Fine. So joule will be cancelled. Second and second inverse will be cancelled. So ultimately the value that you will get, that will be in meter, but we have to express it in terms of nanometer. So that is why finally whatever you will get, you have to convert it to nanometer. So see here what we are getting, 6.63, these two will be cancelled. So what we are getting from this, directly if we write, we will get 3 into, there is minus 34, then plus 19 and plus 8. So if you do this, you will find 3 into 10 to the power minus 34 plus 27. So ultimately what we are getting, it will be 3 into 10 to the power minus 7 meter. Okay, but we have to convert it to nanometer, so that is why 3 into 10 to the power minus 7 multiply with it 10 to the power 9. So when you are converting meter to nanometer, you have to multiply with 10 to the power 9. So ultimately the unit will be nanometer, because if you look at the options, all are given in nanometers. So you cannot express it in nanometer, meter. So if you follow this calculation, first you will get the value 3 into 10 to the power minus 7. But finally, after multiplying with 10 to the power 9, we will get 3 into 10 to the power 2, which means 300 nanometer. So this is the correct option. Next question. A metal surface is exposed to 500 nanometer radiation. So this is the lambda corresponding energy we are providing. The threshold frequency of the metal, that means nu zero value is given, which is 4.3 10 to the power 14 hertz. This is the unit of nu naught. Hertz means second inverse. And the velocity of ejected electron is dash into 10 to the power 5 meter per second. Okay, so here you have to just find the value which will be in this, that is fill in the gap type of question, but it will be integer and nearest integer. Some more informations are also given: Planck's constant and also the mass of electron 9 into 10 to the power minus 31 kg. Here we are going to use the same equation for that we use for photoelectric effect, that is h nu equal to h nu naught plus kinetic energy, which is nothing but half mv square, because ultimately it is asking for velocity, and in half mv square you have the term v. So h nu equal to h nu naught plus half mv square. From this equation, here m is given, which is mass of electron, v is unknown, h we know. Then what is the value of mu naught? That is also given, 4.3 into 10 to the power 14. Okay, and nu value is also given, but directly not given. It is given in terms of lambda, which is this 500 nanometer. So if you write this h nu in terms of hc by lambda, then easily put the value of lambda. So it depends on what type of information given in the problem. Accordingly, you have to choose the formula. If it is that nu value is given, you directly you can use that. If it is given in terms of lambda, you have to write first hc by lambda, then only you can use this equation. So here we will use this equation. We will put all the known values, and from that calculation we can get the unknown value of velocity. So this is the calculation. hc by lambda, while lambda is 500 nanometer, h nu naught, then kinetic energy. So look at the left hand side. This is the value of h, Planck's constant. This is the value of c. This is the value of lambda, but it is in terms of meter. Don't forget to convert 500 nanometer to meter. Otherwise, same, that is SI unit, you have to maintain. Keep that in mind. Convert it to meter. So for that, you have to multiply with it 10 to the power minus 9. Then it will be converted to meter unit. So that is already done here. And in the right hand side, again h. This is the value of threshold frequency nu naught, already given in the question, and half mv square kinetic energy. So after simplifying, you will get this half mv square. This one is actually half mv square. So this is half, then this is m. V square we do not know, and from this other part we have obtained this value. Okay, so now as now you know the mass, you know the rest of the calculation is already done. So from this you can find V will be equal to 5 into 10 to the power 5 meter per second. But we are just interested in this value 5. This is the nearest integer. So this should be your answer. The answer is not 5 into 10 to the power 5. The answer is simply 5. Next topic is dual behavior of electromagnetic radiation. Electromagnetic radiation, you can consider simply light. It can have both wave nature as well as particle nature. Now that is why we are calling dual behavior of electromagnetic radiation. Okay, because we have seen there are some phenomena which we can describe only by the wave property. There are some phenomena, for example, this photoelectric effect, the two problems that we have just seen. So these phenomena can be described only by the particle nature of light. That means both these effects are present, that is particle nature as well as wave nature. So now we can see that this is actually a type of discrepancy, that sometimes it is showing wave nature, sometimes it is showing particle nature. That we already have some experimental proof. So what to conclude? The only way to resolve this dilemma is to accept the fact that dual nature of electromagnetic radiation is present, and it is present simultaneously. Okay, so it possesses both the wave nature as well as particle nature. Okay, now we will see what are the actual findings from this dual nature. So light behave either as wave or stream of particles, and that depends on what type of experiment you are doing. Now when it is behaving as particle, and this particle also have wave nature, this type of particles, there is a special term we use that is known as photons. There is no mass for photon. Its velocity is the velocity of light, 3 into 10 to the power 8 meter per second. Now you will see that among these two different properties, most occasions only one set of properties will be significant. So it is not that there is some experiment, both wave nature and particle properties, you are seeing that both are playing its role significantly simultaneously. So that does not happen. So what happens in most cases, that one set of properties, either wave property or particle property, that will be most significant. Now when particle property is significant, when wave property is significant, that you can understand, the longer the wavelength of the electromagnetic radiation. Now longer wavelength means what? Low energy. So when it is low energy side or low frequency, then more significant will be wave properties. Fine. But on the other hand, if it is very shorter wavelength, that means very high energy, then particle property will be significant. And when it is intermediate wavelength, then it is best considered to be equally significant in both. So these are the ultimate conclusions that we can draw based on dual behavior of electromagnetic radiation. We have seen electromagnetic spectra probably in last class or the class before that, but now we will see different types of spectrum, that is different nature of the spectrum and the corresponding names, continuous and line. First we'll see these two. When light is analyzed passing through prism, it splits into 7 colors, and that is known as Vibgyor. So each of these letter in this word Vibgyor, it is signifying some color. So V, violet, indigo, blue, like this. Okay, green, yellow, orange, and red. So these are the full forms. So when you are passing light through a prism, there will be this type of splitting. Now these colors are so continuous that one is ending, another one is starting, that each of them merges into the next, and as a result you get continuous spectrum like this. So here you can see in the right hand side picture, here we have this white light, and after passing through this prism, it is splitting into 7 colors, and this is known as spectrum. Okay, so violet, indigo, that is V, and then I, then V, G, Y, O, R, Vibgyor. Now you can consider the source as if it is a black body, because black body is such a source. If there is some emission of light, there is complete emission or complete absorption. So if something is emitted from it, obviously it will cover all the frequencies present in it, or all the wavelengths present in it. So it is combining all these wavelengths. So that is why it is ideal source. and whatever light is coming from it, after going through prism, we are getting this type of spectrum. Now it is continuous. You cannot see any split into this spectrum. So one color is ending, then another color is starting. Here there is some line is given so that we can differentiate, but actually no lines are present. So that is why it is continuous spectrum. So all the wavelengths present, or you can say all the frequency of lights present, that is why it is continuous. But what is line spectrum or absorption atomic spectrum? Line spectrum, which is also known as atomic spectrum. Now what it is? So this is made up of distinct lines. When an electron in an atom excites, suppose there is an atom and there is electron present in that atom. So the electron is now exciting and again it is de-excited. So there will be some spectrum. And this type of line spectrum or atomic spectrum, it is having completely different nature, not like continuous spectrum. So that is why the name is different. Now we are calling it line spectrum. Fine. So when line spectrum we are getting, there will be two energy levels. Suppose this is one energy level, another energy level, and the electron in an atom, suppose the electron is present here, now it is going upward. So that is why now it is excited and then it is de-excited. And you are getting this energy difference, which we will get in the form of spectrum. Now under this line spectrum, two types may be there. So under line spectrum, what you can have emission or you can have absorption spectrum. These two types of spectrum you can have. Fine. So details we'll see in the next slide. Now another term you can see in this slide, which is band. We do not have seen this in the previous slide. In previous slide you have seen line and continuous, but now you are seeing something new. So try to understand these three different. Continuous you have already seen. Then line spectrum, it is like this. So you can see it is not continuous. There is some specific colors. So here it is yellow, then we have red, we have blue, like this. And when it is band, it is just like line, but it is wider compared to this line. It is simply a narrow line, but now it is a band like this. Okay, so that is the difference. But it is not continuous. So band is something that you cannot see it is line, because there is some wider band type of nature is present, and you cannot say it is continuous. So it is something as if in between line and continuous. So a line spectrum is a set of discrete wavelengths that are coming from gaseous atoms. Okay, discrete wavelength. That means not all the wavelengths are present. In continuous, all the wavelengths are present. But in this line spectrum, it is some specific wavelengths are present. But what about band spectrum? Band spectrum is basically produced by molecules. Line spectrum is produced by atoms. Okay, band spectrum is produced by molecules. Now in this case, there is a series of closely spaced lines separated by dark space. So as if you have lines like this, then another line, another line. So when several lines are coming together, it will create some band type of nature. Okay, this is a difference. So remember, line is for atom, band is for molecules. And why for molecules it is different, we will also see that reason. So continuous spectrum, it is also known as thermal or black body spectrum. Why it is black body spectrum? Because black body is an ideal body where complete emission or complete absorption is possible. And when I'm saying complete, that means all the wavelengths are present. As all the wavelengths are present, there will be no gap. It will be continuous. So it arises basically from some hot, dense light source. It may be black body, it may be some dense gaseous or solid objects. So these are the source of continuous spectra, because they can emit radiation over a broad range of wavelength. It is not that some specific wavelengths are present, all the wavelengths are present. So that is why it appears as smooth and continuous, and the name is such, continuous spectrum. So line spectra, They are characteristic of elements that emit radiation. But remember, as it is light, that means it is emitting some specific wavelength, not all the wavelengths. So that is why you are not getting continuous. They are also known as atomic spectra that we have seen in the last slide. And the reason is because the lines represent the wavelength radiates from atoms when electrons change from one energy level to another. So it is a transition between two electronic energy level. One is high energy level, other one is low energy level, and in between these two, when the electron it is going from low ground state to high energy state, this energy gap, the corresponding wavelength only you can see. And what about band spectra? As it arises because of molecules, so that is why it is also known as molecular spectrum. So one thing I want to mention, that sometimes you are seeing that spectrum and sometimes it is spectra. Actually, one is plural form, another one is singular form. That is the only difference. Fine. So this band spectra, or another name is molecular spectra, they are produced by molecules. And here, not only electronic transition that you have seen in case of line spectrum, as it is mentioned here in the previous line, but now some extra transition is also possible. So what are those? Now rotational energy level, vibrational energy level, these are also present, and there is some extra transitions possible. So as there are some extra transitions, not just transition between two electronic energy level, you are also getting rotational transition, vibration transitions. That is why some different types of wavelengths are also present, and that is the reason now you are getting some band type of nature. But remember the important difference: line spectra obtained from atoms, band spectra they are obtained from molecular gases. It may be that is any molecule, suppose diatomic molecule or triatomic molecule, ozone, nitrogen, like this, or it may be some chemical compounds. So it is actually molecule, not a single atom. That is the difference. In the next slide, we will elaborate what is electronic state, then what is vibrational transition, what is rotational transition. So all these things you can understand from this picture. So here if you just focus on this blue line, it is basically the excited electronic state. The lower one is ground electronic state, this blue line, and the upper blue line, that is excited electronic state. So this gap, which is denoted by this red colored arrow, this gap is because of this electronic transition, which you see in case of line spectrum or atomic spectrum. Now, if you just focus on this one ground electronic state, within this one ground electronic state, we have different types of vibrational state, which are shown here by the green line. Okay, so this type of transition that you are seeing, this corresponding energy gap, suppose here energy gap is daily V I am writing because it corresponds to vibration. So this energy gap, it will be having some specific wavelength. Now within this vibrational level, there are some rotational levels also, which are shown here by these red lines. So transition between these two, any of these two red lines, that will give some energy change. Suppose that is del E R. Okay, and this energy gap del E electron. So E small e I have written. So different types of energy gap involved. That means different types of lambda will be there, and only in molecules you can get this type of rotational transition or vibrational transition, because rotation vibration, it is not possible in a single atom. It is possible only in a molecule where two atoms are connected together or three atoms are connected together. Then only the question of rotation or vibration arises. So when it is a simple atom, that is single atom, suppose just simple hydrogen, there is no question of rotation or vibration. So rotation vibration, this question arises only for molecules. Fine. So this is the reason why line spectrum, it is simple, because only you have these two energy levels, this blue one and this blue one, and the corresponding energy. So that is why you are getting very single lines, okay, but not for molecules. For molecules, rotational transition, vibrational transitions are also involved. So line spectra resulted from atoms. Atoms have electronic energy levels, not rotational or vibrational. So here absorption or emission involves a transition between discrete state, and there is no other possibility. Okay, so if it is absorption, that means electron going from ground to high energy state. If it is emission, it is the opposite process. From high, now it is going towards ground state. And band spectra, it is because of these molecules. Molecular species contain vibration rotation energy levels associated with electronic levels also. So transition can occur from an end to any of these level. Okay, so several other possibilities are now present. So this is a difference. So this unlimited number of possibilities and unlimited number of transitions, that will give an absorption emission continuum, that is something like band, and this continuum is actually band. So this is the reason why you are getting only line spectra when it is atoms, but not for molecules. Now for molecules there is band. So here we will see some important difference between line spectra and band spectra. Line spectrum is the characteristic property of atoms, but here it is for molecules. Line spectra contains sharp and distinct lines that you have already seen. Band spectrum contains group of lines together, so that is why it appears at continuum or band. It is formed during excitation and de-excitation of electron in the atom, and when it is band spectrum, that is for molecules. Some other type of transitions are also possible. Vibration, rotations, these are also possible, because now we are dealing with molecules. Okay, so these are the important difference between line and band spectrum. Emission and absorption. So once you know this line spectrum, it can be two types, emission and absorption. And spectra, as we can classify under these two broad categories. An emission spectrum consists of all the radiations emitted by atoms or molecules. Fine. Whereas in an absorption spectrum, though here it is mentioned atoms and molecules, but mostly we see emission and absorption only for atoms. So whenever that is here, the pictures that I will represent, you will see that is only line spectrum. That is line spectrum type of emission spectrum, and line spectrum for absorption, not for molecules, will be shown, but it is possible for both of them. So see, emission spectrum consists of all the radiations emitted by atoms or molecules, but when it is absorption, as if, just consider there is a continuous spectrum. Fine. As if a portion of this continuous spectrum, which is another way you can say light containing all the wavelengths. So light containing all the wavelengths, now some wavelengths will be missing in the continuous spectrum. So that is the difference. So when it is emission, there is some discrete wavelengths will be present. So you will see in the black background, there will be some colored lines. But when it is absorption, just take any continuous spectrum, but there will be some line in the color, in the form of line, some colors will be missing. Okay, because now they have been absorbed by the medium through which light has passed. So suppose the light has passed through some sample, and in the sample, whatever substance is present, it is absorbing some wavelength. So in the continuous spectrum, some wavelength will be missing. Okay, so now we will elaborate it separately, and we will also see the picture. So see, when it is emission spectrum, it is having some bright lines in some dark background. Okay, so we have some hot dilute gas. It is emitting some radiation, and this radiation, when going through prism, you are getting this type of spectrum. Spectrum of radiation emitted by a substance that has absorbed energy. So first, this hot dilute gas, it has absorbed energy, but now it is now emitting those radiation. But this emitting radiation, don't think all the wavelengths are present. It is only some specific wavelengths are present. So that is why we are getting only lined type of nature. It is noticed when radiation emitted from source are passed through a prism and received on photographic plate, then we can get this type of emission spectrum. Okay. What about absorption spectrum? Absorption spectrum is a spectrum obtained when radiation is passed through a sample. Now we have taken a black body, and we know black body, it is emitting that radiation which will contain all the wavelengths. Now this all wavelengths, when it is going through some cool gas, it is absorbing, depending on the substance that is present in this cool gas, it will be absorbing some wavelengths. So first, from this black body you are getting all the wavelengths, then some wavelengths are missing because it is absorbed by this gas, and then when it is going through prism, finally the spectrum, it will have this type of nature. So it is just like a photographic negative of an emission spectrum, right? So now you are getting some dark lines. So these are the missing wavelength. This is a missing wavelength, missing wavelength. Okay. Dark lines on a bright background. This is the difference between emission and absorption. Line spectrum of hydrogen. So now we have taken specifically hydrogen atom, and when hydrogen gas present on discharge tube passed through high voltage and low pressure, then we get some radiation. So this emitted radiation passing through some spectroscope. So this is an instrument which is used in spectroscopy. Pass through some spectroscope. It helps us to analyze the spectrum. Fine. So finally, the spectrum that we are getting in the photographic plate, it will be having this type of nature. Okay. So hydrogen spectrum contains several lines, and these lines known as series. So after going through prism, there is a black background, so it is basically emission spectrum. Though it is not mentioned, but you can understand from the picture, it is emission spectrum. We have some colored lines in the black background, so it is emitted radiation. Fine. So 4 lines are mentioned here: 1, 2, 3, and 4. So the violet, which is 410 nanometer, very low wavelength, that means it is the highest energy. Then 434, the next lower energy. 486, the next lower energy, and then this one. So suppose it is lambda 1, lambda 2, lambda 3, lambda 4. Okay, this type of specific lines we are getting on the black background. Fine. Now this picture, you can also imagine it. Suppose we have this hydrogen atomic model. There is nucleus present in the center, and these are the the first energy level, then second energy level, up to energy level 6. So suppose electron is coming, suppose the electron is present here, and as it is emission, so obviously from high energy level, now it will be going towards low energy level. So electron from 6, now it can go to n equal to 1. Then from n equal to 5, it can go to n equal to 1. Then it is 4, then 3, then 2. So it may be 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1. All these are the different possibilities. Similarly, so here the last level, that is common. So all these, that is in all cases, electron is coming to n equal to 1. Similarly, if you fix this last energy level, which is n equal to 2. So now the electron is coming from 6 to 2, then 5 to 2, then 4 to 2, and 3 to 2. That means from different high energy, now it is coming to a common energy state, which is level 2. Similarly, from 6 to 3, from 5 to 3, from 4 to 3. Okay, you can also consider the next possibilities. That means 6 to 5, 6 to 4, then 5 to 4, and then the next one 6 to 5. So depending on the last level, or you can say n lower, one is n higher, so in first case n lower is n equal to 1, then n lower is n equal to 2, n lower is n equal to 3. So depending on what is n lower, we can have different types of series. So when n lower is 1, that is n1, then there will be one type of series, and in that series, common thing is that whatever is the high energy state, it is always coming to n equal to 1. Then for n equal to 2, then there will be another series with different name. So the common point is whatever is the high energy state, it will always come to energy level 2. This picture you can also represent in this way, and it will be easier for you to understand it here. So see, when it is ending to n equal to 1, that means n lower is the first level. So this is the ground state here, and these are the different possibilities: 2 to 1, then 3 to 1, 4 to 1, 5 to 1, okay, and 6 to 1, and so on. So this is known as Lyman series. Then when it is n lower, n equal to 2, possibilities are 3 to 2, 4 to 2, 5 to 2, 6 to 2, like this, which is represented by these pink lines, and it is under Balmer series. Okay. Then Paschen series, bracket series, Fund series, following the same type of neat format. Fine. Now this series, if you watch properly, as we are moving from Lyman to Balmer to Paschen to bracket to Fund, the energy gap, just look at these blue lines, the energy gap is very high. Then go to pink one, it is slightly less. Go to green, it is further less, and gradually it is less and less. So maximum energy that you can expect for Lyman. So this series, it can be expressed by this common equation, which is 1 by lambda, or you can write mu bar, because mu bar is 1 by lambda, that is equal to RH, where RH is a constant having 109677 centimeter inverse. So this is the value of RH, which is basically a constant. Then in the bracket you can see 1 by n1 square minus 1 by n2 square. So here n1 is basically the lower, that is to which the electron is ultimately reaching, and n2 is higher. So n1 lower means 1 by something lower, obviously denominator lower for 1 by n square. But compared to 1 by n square, if you consider 1 by n2 square, as n2 is always greater than n1, so 1 by n2 square, it will be small. So we can say as n2 is always greater than n1, so 1 by n1 square, that will always be greater than 1 by n2 square. So that is why this total quantity within bracket, it is always positive. But if you write 1 by n2 square before, now it will be negative. So how you are representing the equation? Be very careful. If you are writing 1 by n1, where n1 is a lower level, then obviously this overall term will be positive. Now some more information. When it is Lyman series, we know it is n lower is fixed at 1, n2 it may vary 2, 3, 4, 5, and so on, and it falls under UV. Next series falls in visible, and the next 3 series infrared. And we know UV energy, it is greater than visible, which is greater than IR, infrared. That means for Lyman it is maximum energy involved, then for Balmer it is gradually less, and then for these 3 it is even lesser. Okay, so you can get question regarding this, as if series is mentioned, then it falls under which region of spectrum, UV, visible, or IR. So here this equation that you are seeing, you have to use it several times while solving problem, so you have to memorize it. And here n1, n2, all these are integers. So finally the 1 by lambda in the left hand side, we know it should have unit distance inverse. So see, in the right hand side also unit is centimeter inverse. It may be meter inverse also, but important thing is it is distance inverse. If you want to know RH elaborately, then Rydberg constant is basically this. It is coming from MeE4 divided by 8 epsilon square H3C. Okay, where M is mass of electron in kg, E is charge of electron in coulomb, then vacuum permittivity C square per Newton per meter square, Planck's constant, and C. These two you already know. If you put all this, you will get the value of Rydberg constant in SI unit. Now look at the value, it is in meter inverse. When it is centimeter inverse, it is basically 109677. And now it is 10 to the power 7. So if I write it like this, 10973, 3 more zeros. Okay. So here we have total 6 digit. Here we have 2 more. So obviously it has to be, because when it is per centimeter, the value is less. When it is per meter, the value is high. Okay. Now we will solve this problem, which is based on this equation. So I already have this that you have already seen in the previous slide. Already I have presented it here so that you can solve the problem easily. The question is saying that the region in the electromagnetic spectrum where the Balmer series lines appear, it is visible. Okay, so correct option C. Very easy. Next question. If the shortest wavelength for hydrogen atom, shortest wavelength is minimum energy. If the shortest wavelength of hydrogen atom in Lyman series, look at the Lyman series. It involves emission 2 to 1, 3 to 1. Now when it is 2 to 1, obviously the energy gap, and when it is 3 to 1, now the energy gap, it will be high. But it is mentioned shortest wavelength, sorry, it is maximum energy. Now maximum energy means what? N2 must be infinity, right? Then only maximum is possible. Suppose this is N1, this is 2, then 3, then 4. Then in this way there will be some infinity. So this gap is maximum, and we have to consider maximum energy because it is shortest wavelength. So that is why N2 will be infinity. So if under this condition the shortest wavelength is X, you have to find from this information the longest wavelength for Balmer series. Now for Balmer series, longest wavelength means minimum energy you have to consider. Okay, so 3 to 2, 4 to 2, 3 to 2 obviously minimum energy. So now you have to put N1 is 2, N2 is 3. Okay, options are there. So what we will do, you have to follow this formula, just a little change is there. And what is this change? In the previous equation, see, in this equation it is actually for hydrogen atom, and we know for hydrogen atom Z is equal to 1. So that is why no Z is mentioned. But in general, if you write, it should be RH into Z square, because in the question it is asking longest wavelength in Balmer series, not for hydrogen. It is for helium plus. Now helium plus is also one electron system, just like hydrogen. You know, helium is having configuration 1:2. That means when it is plus, it is actually 1:1, which is just like hydrogen. So this is also one electron system, but difference is now Z value you have to consider, and Z for helium atomic number is 2. So that is why we are now using a little changed equation, which is now having this Z square. So Z for hydrogen it is 1. So first, for Lyman series, as we have to find maximum energy, so N2 is infinity, N1 is simply 1. So if you put infinity, this part will be 0. Z is 1. So ultimately what you will get? You will get 1 by lambda equal to RH. Fine. That means 1 by lambda is 1 by x. So 1 by x is equal to RH. So this is the value of Rydberg constant. Z is 1. Same thing you have to do for Balmer series. And also remember, it is not for hydrogen, it is for helium. Now for Balmer series, N1 is 2. Lambda is longest, that means minimum energy which is possible when you consider N2 3. And Z is 2. So RH value we have calculated is 1 by x. Z squared is 4 because it is 2 square. Then 1 by 2 square, 1 by N1, N1 is 2. 1 by N2 square, which is 3. So ultimately what you get within bracket, it is 5 by 36. If I write the calculation, it is basically 1 by 4 minus 1 by 9, which is giving you 9 minus 4 divided by 36, which is nothing but 5 by 36. Okay. So 1 by x, which is the value of Rydberg, multiplied by 4 multiplied by 5 into 36. So 1 by lambda max, because we have to find the longest wavelength, that is maximum, that is equal to 5, 4 and 36, it will be 9. So 5 by 9x, that means lambda x is 9x by 5. So correct answer is this one. Next question. For the Balmer series, in the spectrum of hydrogen, nu bar is equal to, this equation we already know. Now remember, based on Balmer series, you have to check the correct statement. So which are correct statement? There are total 4 statements given. 1, 2, 3, 4. It is a single choice answer, but in different options 1, 2, 3, 4, several statements are present. 3 statements. Different combination of 3 statements. 1, 3, 4, 1, 2, 3, 1, 2, 4, 2, 3, 4. Okay. So for Balmer series, we know N1 is 2 and N2 is 3, 4, 5 and so on up to infinity. So for this, we have to consider this statement one by one. So we have to focus on this. The first statement is saying, as wavelength decreases, the lines in the series converge. Now see, remember the lines are like this. Suppose if it is first energy level, then second energy level, third, and gradually it is becoming closer and closer. If you look at the energy levels, you can see that. Just have a look. Here you can see, as you move from 1 to 2 to 3, gradually the energy gap between this individual, it is decreasing. So this gap between 2 and 1 is very high, but the gap between 6 and 7 or 5 and 4, gradually it is decreasing. So just keep that in mind. So if it is so, as wavelength decreases, that means as energy increasing, as wavelength decreasing, that means as energy increasing, the lines in the series that will converge. So if you consider the first transition, that is 2 to 1, and if you consider the other transitions, that is suppose it is 6 to 1. Okay, so now if you look at the spectrum, gradually you will see the lines are getting closer and closer. That means it is converging to each other. Okay, so here energy gap is low, but if you consider from some high energy level to this, because as wavelength decrease means as you are going towards high energy transition, 6 to 1. First suppose it is 2 to 1, there is one energy, then 3 to 1, some higher energy, then 4 to 1, some higher energy. That means gradually the wavelength is decreasing. So the corresponding nature of the emission spectrum, it will be like this. So this statement is basically true because it is converging, coming close to each other. Okay. Then the next statement, the integer n1 is equal to n2. Now this is true because for Balmer we know n1, that is n lower is 2. So first statement, second statement, both are correct. Based on this, you can see, you can maximum cancel first option, but you are now also, okay, you can also cancel this one. If you are sure about this, now you are stuck between option 2 and option 4, sorry, option 3. Because we already know first and second statement same. First and second statement true, and that is present in option 2 and option 3. So option 1 and 4 you can cancel. Come to third statement. The line of longest wavelength corresponds to n2 equal to 3. Longest wavelength means what? Minimum energy. Now for Balmer series, this 2 to 3, that is minimum energy. So this is also correct. Now 1, 2, 3, if you are sure that it is correct, even you don't have to consider statement number 4. Based on this, you can easily choose correct option as the second option. But we will also see why the last statement is not correct. This is very interesting. So last statement is saying the ionization energy of hydrogen can be calculated from wave number of these lines. Now ionization energy means what? For hydrogen there is only one level, right? That is only one electron in 1s. Though if other energy level, if it is present, then also there is no electron. Now ionization energy, if you consider the definition, the minimum energy required to remove the valence electron, in this case there is only one electron. The most loosely held electrons to infinity, that required energy is ionization energy. So in this case, N1 is 1 because the other levels there are no electron, and you have to consider ionization energy. So you are now fixed to N equal to 1, and you are applying that energy when electron is going to infinity. So if you maintain this condition, you cannot obtain from Balmer. Why? Because in Balmer, N1 is fixed to 2 value, but for hydrogen it has to be 1. So you cannot calculate wave number, that is nu bar or 1 by lambda, from this equation, right? So this statement is not correct. So we can obtain ionization energy by putting N1 equal to 1 into infinity, then only you can get ionization energy. But remember, here N lower must be 1, which is present in Lyman, not Balmer. In Balmer it is fixed to 2. So that is why this statement is false. This is true, this is true, this is true. So keeping all this in mind, correct option will be option 2. For any given series of spectral lines of hydrogen atomic hydrogen, let del nu bar is equal to del nu bar is equal to nu bar maximum minus nu bar minimum, or you can say 1 by lambda max minus 1 by lambda minimum. Be the difference in maximum and minimum frequencies in centimeter inverse, because it is nu bar, so unit will be centimeter inverse. Okay, so this del nu bar you have to find for Lyman, you also have to find it for Balmer, then take the ratio. So you have to find that ratio. Options are there. Okay. So again, we will take the help of this Rydberg equation. So nu bar max, or you can write 1 by lambda, but here nu bar is required. So when it is Lyman, we know n lower is 1, and as it is maximum nu bar means maximum energy, because nu bar is inversely proportional to lambda. So the relationship of lambda and energy is inverse. So relationship of nu bar and energy, it will be direct. So nu bar max high means that is max, as it is saying. Obviously the energy is also max. Now energy max when it is possible? When n higher level is infinity. So nu bar max for Lyman is RH. Nu bar mean for Lyman is now n higher is 2, because this is fixed, you cannot change it. But now n2 is 2. It starts from that is 2 to 1, 3 to 1. So 2 to 1 is the minimum energy, because nu bar is minimum. And this is 3 by 4, which we are getting, that is the term within bracket. Now if you take this ratio, that is nu bar max, sorry, not ratio, nu bar max minus, that is RH, minus 3 by 4 RH. So what you will get? 1 by 4 RH. Okay, same thing you will do for Balmer also. Now for Balmer, N2 is fixed as 2. Similarly, as you are finding nu bar max, you have to put infinity. So you are getting RH by 4, because this part is 0. Then for minimum energy, you have to consider higher level 3 to 2. So it is 1 by 4 minus 1 by 9, which is 5 by 36. So now del nu will be RH 4 minus 5 RH 36. If you do the calculation, it will be 36 is 9 minus 5. That means you are getting 4 by 36. So 4 by 36 is nothing but RH by 9. Okay. So nu bar Balmer is RH by 9. From this calculation, now take the ratio nu bar Lyman divided by nu bar Balmer. Nu bar Lyman is already calculated, which is RH by 4. This is RH by 9. So ultimately it will be 9 by 4. So this should be the correct option. Option D. Okay. So we will end here. Thank you for listening.